when we apply a magnetic field into a current carrying conductor perpendicular to current, the charges are experience Lorentz force and take separate to each other and create a transverse voltage is known as Hall voltage, right? You already know that classical Hall effect. The system is in a thin two-dimensional material in which it is restricted to move in two dimension. So the motion is confined to a plane. Let it is x direction. Let the current is x direction, the magnetic field is negative y direction, and it is also called two-dimensional electron gas. Okay, in presence of magnetic field nearly 5 to 30 Tesla, which is perpendicular to the plane. This is a plot of rho xx and rho xy versus magnetic field. Let me point out which are rho xx and rho xy. Let the current is in the direction, okay, and there is a voltage that is developed of segregation of charges and it's called Hall voltage. There is also resistivity in that direction of current, that is rho xx, which is generally called longitudinal resistance, also called magnetoresistance. There is another one called transverse resistance, that is rho xy, also called Hall resistivity. For rho xy, there is some plateau at some integer value I is equal to 2, I is equal to 3, I is equal to 4, and so on. These are in units of h over e square. The Hall resistivity of this plateau, is 2h over e square. Here this plateau 3h over e square, this plateau 4h over e square, and these integers are independent of material. So again, the longitudinal resistance is 0 most of the time, but it shows peak as the Hall resistivity make a transition from one plateau to another plateau. You see the longitudinal resistivity shows 0, which means it is a perfect conductor, and suddenly resistivity increases, which means it is an insulator. So the system is undergoing a transition from insulator to metal, so on. There are some interesting features of quantum Hall effect. The Hall effect, where the charges migrate to different edges of the sample, but here I am going to talk the same effect with the spins, that is spin up and spin down will segregate two edges to the sample, give rise to a spin Hall effect. Okay, so we have seen in quantum Hall effect the resistivity occurs is multiplied over h over e square. Those come from the bulk boundary correspondence. The system will only conduct through the boundary and the bulk remains completely insulating. The physical picture is two-dimensional electron gas, and we have the bulk where the electron execute cyclotron motion while it keeps along the edges, conductance takes place, and that orbit is called skipping orbit, right? The distinctness in the behavior of the bulk and the edge state yield a name topological insulator. Since 1980, there was a search for another class of topological materials where similar bulk boundary distinction exists. It is realized that a time reversal invariant term can achieve this. This eliminates the uses of magnetic field, which evidently would violate time reversal invariance. That effect is spin Hall effect, which is basically describe the fact that a spin current is generated perpendicularly to an electrical charge current in a metallic wire. That is, when an electron current flows through the wire, spin is accumulated at the side of the metallic wire. You can see the animation. These are unpolarized electrons are interact with the static electric field of that defect, produce a effective magnetic field. That effective magnetic field interact with the spin of that electron and coupling with the spin. That coupling is known as spin orbit coupling. Due to spin orbit interaction, the unpolarized spin starts precision about the effective magnetic field, right, and will become polarized, and spins are scattered by that defect due to spin orbit interaction and separate to opposite edges of the sample. Here the formation of effective magnetic field is totally a relativistic case. The theory of relativity states that a particle moving in an electric field experiences an effective magnetic field which is perpendicular to particle movement direction. The interaction of this effective magnetic field with the spin is called spin orbit interaction. It is important that the direction and magnitude of the effective magnetic field does not depend either on the particle charge or on the particle spin, and that effective magnetic field act on the particle magnetic moment and causes the precision of magnetic moment around the direction of effective magnetic field. These are some mathematical calculation. It is a relativistic case. So in a particle is moving in one direction, this is a one type frame of reference. So the particle observe the effective magnetic field which is a totally relativistic case, that is B prime is equal to gamma multiply with B minus V over C square into E. Okay, so let B is equal to 0. Let there is no magnetic field, so B prime becomes gamma whole into minus B by C square into E. So the Hamiltonian becomes spin orbit Hamiltonian becomes, we know already, the dot product with the magnetic moment with the magnetic field. So again we know mu is equal to minus G mu B sigma, where mu B is the Bohr magneton, sigma is the spin of electron, right? So G is the another constant factor. So Hamiltonian becomes by putting this value in that equation, minus G mu B P by C square sigma whole into B cross E. By mathematical calculation it is becomes the all term are constant, so constant we can convert this term into this sigma cross B dot E. Okay, so how can we observe the scattering process in the mathematical equation? So HSO becomes constant whole into sigma cross K whole into del V, where E is equal to del V. Again, okay, so here the Hamiltonian equation. So here is a defect. Okay, let a spin of electron which moves in this direction. Let the direction this is the direction of K, propagation vector, right? So sigma is the spin, so K is the direction vector. So Hamiltonian direction becomes both. So in this equation H becomes perpendicular to sigma and K. That means H becomes perpendicular to that spin and that K vector, which is basically in this direction. So the spin of electron will scatter in that direction. Okay, so similarly spin down electron, and this is the propagation vector, and that perpendicular component is in this direction. So the particle spin down particle will scatter in that direction. So this is the process of separation of spin up and down electron. Okay, so okay. So how does a spin interaction makes electron scattering spin dependent and direction dependent? After scattering by the defect, let the effective magnetic field in the left hand side is off direction, right? The probability is more for that electron is going to left because of same direction of electron spin with the effective magnetic field. The probability is less here to going right hand side because of opposite sign, and so the electron will move basically as a result, so the electron will try to move in the left hand side. Okay, similarly in case of downspin electron, the probability of scattering downspin electron towards the right is more because of spin direction, and the effective magnetic field direction is the same. So the as a result particle will try to move in the right hand side. Okay, due to such dependency of scattering, an electrical current flowing along a metallic wire creates a spin polarized current which flows perpendicular to the wire. This is a animation what I have told. these electrons going that direction and interact with the static electric field of that effect. So the probability of that electron going to that direction is high. So and similarly the electron going to this direction because of more probability of scattering. These are also understand by using energy distribution function. Here is the energy distribution function. Let a particle does not interact with any defect. This is the energy distribution function versus energy diagram. We know here in case spin of electron, the probability of scattering that electron towards left is high because of same direction of spin and effective magnetic field. And also we can observe by energy distribution function, by the spin orbit interaction, the energy of the particle towards left side is decreased by the amount of mu h. Okay, towards right the amount of energy is increased by the amount of mu h. So we know electron will try to always occupy the lower energy state. So electron will try to move in that lower energy state. So the probability of scattering that electron will left side is maximum. Similar for downspin electron, the scattering probability of right side is maximum. So this is the case. So this is all about the spin Hall effect mechanism and the first observation. Okay. So this is the first observation by YK and DA and colleagues at the University of California. The experiment was based on an core rotation. Okay, where what is core rotation? Now where polarization of light beam rotates when beam reflects of a material, right? The amount of rotation is proportional to the magnetization of the material. So by measuring the amount of core rotation, we can determine the relative number of spin up and spin down electron. And this is the experiment that they had done. The laser pattern into 300 into 77 micrometer square of gallium arsenide and n-type indium gallium arsenide. Okay, the channel. And electric field was applied along that channel, while the magnetic field B could be applied perpendicular to that channel. So this is the scanning report. It shows two-dimensional scan of gallium arsenide sample, which demonstrates the existence of spin accumulation. Here the red mark indicates the spin of electrons are accumulated that side, and the blue mark indicates that the spin down electrons are accumulated of that side. This is the scanned copy, and the polarization has opposite sign at the two edges and decreases rapidly with the distance from the edge as expected for the spin Hall effect. This is further experiment by increasing the external magnetic field, and this is the spatial dependence of peak core rotation A0 across the gallium arsenide channel. So this is all about spin Hall effect and its first experiment. So which is it totally depends upon spin of electron. So if relate to an electronic symbolism, that is spintronics, there is three main advantages of spintronics over electronics. Is first is spins have no Joule effect, no Joule heating, and second one is spins do not scatter by impurities, and third one is dissipation-less communication. Okay, in spintronics, recently researchers explored the spin of electron as well as the charge and create a separate device which is more functionality. Okay, then several applications already employ such spin dependent effects such as spin valve, read heads that have enable higher data storage density in hard disk drive. Another example is magnetic random access memory, which is able to store information even when all the electric power to a device is switched off. So these are my reference. Thank you.